Alright, let's start by looking at what transfer learning actually is. So, in machine learning, instead of training a model from scratch for every new problem, what we often do is reuse a model that's already been trained on a different task. Usually, that first task was trained on a large dataset like ImageNet, and these models have already learned useful patterns. I mean edges, textures, shapes, all that early stuff. The idea is if those features are relevant to our new task, then we don't need to retrain everything from zero. We just start from that existing knowledge and build from there. And it is especially helpful when we don't have that much labeled data for the new task. Instead of collecting thousands of new examples, we take what's already learned and just adapt it a little bit. Now, down here you can see how the training process actually works step by step. And first, right now, we are in the extract feature step. This is the part where the pre-trained model takes input images and turns them into feature maps. If we have chosen to freeze some of the layers, and we'll talk about it later, then those layers don't change during training. They just act as fixed extractors. It is like saying, hey, I already know how to detect curves, edges, textures. No need to retrain me on that. Then we move to the next step, forward pass. You can see. And here the data flows through both the frozen layers and whatever new layers we have added on top. These might be fully connected layers or whatever architecture we have built for the new task. The goal is to generate predictions based on those extracted features. Basically, this is where the model takes a guess. Once we have the prediction, we need to check how good or bad it is. That's where the compute loss step comes in. Third, you can see here. The loss function compares the model's predictions to actual labels. It gives us a number that tells us how far off we are. The bigger the number, the worse the prediction. That number becomes a signal we use to correct the model. And now, the last step here is update weights. This is where optimization kicks in. The model adjusts the weight of whatever layers are still trainable, mostly the custom head and maybe some of the deeper layers in the base model if we have chosen to unfreeze them. The optimizer uses gradients to figure out how to tweak those weights so that the loss goes down next time. And just notice something, when we reach this phase, we are no longer just doing feature extraction. Now we are in the fine-tuning stage. Okay, and as you can see, the learning rate also drops. It goes from 0.001 to 0.0001 because we are making smaller adjustments. Okay, we don't want to mess up what the base model already knows. Okay, and let's take a look at the pre-trained model options. Here we have selected VGG16. That's one of the older classic architectures. It is deep, has a lot of parameters, but it is easy to understand and works well when you don't need all the tricks of modern networks. You could also pick something like ResNet 50, which uses skip connections and tends to generalize better, especially if you are working with more complex datasets. Or MobileNet, which is much lighter and designed for lower resource environments, like if you are deploying the model on mobile or embedded systems. And choosing the base model depends on what kind of task you are dealing with, how much compute you have, and how big your dataset is. And I think it's okay, and let's continue. Here, the first control we have got is this one, freeze layers. What is that? 4. Okay, right now it is set to 4. What that means is the first 4 layers of the pre-trained model, in our case VGG16, remember, are frozen. They won't be updated during training. These frozen layers will act like fixed feature extractors, which is useful when we think those early features like edge detectors or basic patterns are general enough and don't need to be retrained. And freezing some layers can also help avoid overfitting, especially if you don't have that much data in the new dataset. And it reduces competition too, which is nice if you are limited on time or hardware. Okay, now speaking of the dataset, let's take a look at the target domain we are working with. In this setup, we have selected a dataset called animal species. You can see here. And this one is marked as high similarity, which refers to how closely related it is to the source domain. In this case, the source model was trained on ImageNet, which already includes lots of animal classes. So yes, there is a good overlap in terms of visual patterns, shapes, textures, colors, which makes transfer learning more effective here. And you will notice there are other options too, like medical images, which are marked as low similarity. That's a tougher case because the domain is quite different from ImageNet. So models might struggle more and need heavier fine-tuning. And alright, that's okay, I hope. Moving on, we also got some optimization settings to check. And you can see the first one is the learning rate. Right now it is set to 0.001, which is a typical value during the early phase, especially when we are just training the custom head or updating a few layers. Later, during fine-tuning, this is usually lowered. We will probably go down to something like 0.0001 just to avoid overwriting useful weights from the pre-trained part of the model. Okay, then we have got the batch size. This one's currently set to 32, which means that 32 images are passed through the model before the weights are updated. Larger batch sizes are more stable but need more memory, and smaller batches are noisier but they tend to generalize better. You can adjust this depending on what kind of hardware you have and how the model behaves. And here's the important bit, the connection between source and target domains. So the source domain here is ImageNet. That's over 1 million labeled images across 1,000 classes. The target domain we have picked is animal species, 8,000 images across 20 classes. Now, since both datasets contain animal images, the model doesn't have to relearn everything from scratch. It just needs to adapt what it already knows to the new set of labels and maybe different image style. That's okay. And I'm looking, what can I say? This is the core idea behind transfer learning. Reuse what's useful, adapt the rest. And let's go down and take a look at the model architecture. We are using VGG16 here, and you can see the breakdown clearly. Here 17 layers in total, and out of this 4 are frozen and shown in purple here, and here 13 are trainable in green. So around here 76% of the parameters are still being updated. That gives us a decent balance. We keep some of the early structure, but we also give the model flexibility to learn new patterns when needed. Below that, you can see the custom path we have added. Okay, this set starts with a global average pooling layer, which reduces the feature map size while keeping spatial information. Then there is a dense layer with Here you can see 256 units and value activation. After that we have a dropout layer to reduce overfitting, and finally there is the output layer, which in this case has 20 units, one for each animal class, using softmax activation to turn the logits into probabilities. And this setup is pretty standard when you are doing classification with transfer learning. You extract features from the base, pass them into a few new layers, and train just that part, or some of the base layers as well, depending on how complex the target task is. And here we can see an example for performance features. Here training accuracy and validation accuracy. It is just an example, and here you can see bar charts, learning curves, accuracy, loss, and here blue, orange, and pink, purple for training validation. Okay. Alright. Let's pause here and talk through a few key concepts that come up often in transfer learning. We will start with feature extraction. The basic idea here is that we freeze the pre-trained model and just use it to generate features from the new data. Then we only train the new layers we have added, usually a classification head. This works well when the target dataset is small or visually close to the source domain. We are not changing the base model at all, we are just using it as a ready-made tool to get the initial features. Now, if we move on to fine-tuning, that's a bit more flexible. Here we allow some or all of the pre-trained layers to continue learning, but we typically lower the learning rate. Why? Because we don't want to erase everything the model has learned. We just want to adapt it slightly to the new domain. And this is especially useful when the new dataset is larger or the domain is not an exact match. Okay. And then there's domain adaptation. So what does that mean? Well, sometimes the source and target data look quite different. Maybe the source is natural photos, but the target is X-rays. In those cases, a direct transfer doesn't work very well. Domain adaptation includes techniques to narrow that gap, so the model can still generalize. It's kind of like adjusting the model's expectations about what kind of data it is seeing. Okay. Now let's walk through the main strategies people use when applying transfer learning. Let's look at this. One is the classic, just freeze everything and only train the new heads. Another one is full fine-tuning, where all layers are updated. Then there's progressive fine-tuning. You start by freezing everything and then gradually unfreeze layers during training. There is also multitask learning, and where the model learns multiple related tasks at the same time. That can help it generalize better across domains. Domain adaptation we already touched on. That's when the data distributions differ quite a bit. And finally, layer substitution. These ones a bit more advanced. Sometimes people swap out certain layers in the base model with new ones that better match the target task. Alright. What about where transfer learning is used? One obvious area is computer vision. Tasks like image classification, detection, segmentation all benefit from it. Another one is NLP, text classification, translation, summarization. All of these often start from large pre-trained language models. Okay. Medical imaging is another big one, especially when there is limited labeled data. Speech recognition also fits in there, like adapting a model trained on one accent or language to another. And RL here, in reinforcement learning, it is used to transfer policies between tasks, say from one type of game to another. And in low resource domains like rare language or narrow technical fields, Transfer learning is sometimes the only realistic option when you can't afford to collect huge datasets. Okay, so what's the point of doing all this? What do we actually gain? And first, it reduces how much labeled data you need. You don't have to start from zero. Second, it cuts down on training time. The model already knows quite a bit, so you are just tweaking it. It also tends to give better performance on tasks where you don't have enough data to train from scratch. And it helps avoid overfitting, especially when you freeze some layers and only train the parts you need. Of course, there are trade-offs you can see. And one problem is something called negative transfer, that when the source and target are too different and trying to transfer actually hurts performance. Also, choosing how many layers to freeze is not always obvious. If you freeze too many, the model can't adapt. If you unfreeze too much, you might overwrite useful knowledge. Then you have to find the right learning rate or fine tuning. Too high and you mess up the pre-trained weights. Too low and training becomes slow or ineffective. Big models also need serious compute. That's another practical barrier. And sometimes your input data just doesn't match the shape or format of the base model. I mean, you need to make architectural changes, which adds extra work. And lastly, there is always a balance between keeping what the model already knows and allowing it to learn new patterns. That tension is part of what makes transfer learning both powerful and a bit tricky to get right. And that's all for this lesson. Thank you for listening.